Okay, cool. We are live. Hello, everybody. I think we've got people coming on now. So, hello, everyone. I am James. I'm kind of the Lambda Lounge portion of all of this. So we've got probably quite a mixed audience tonight of kind of our regulars who are Manchester-based people. Hello, and then some people from the Scala community. And for those people, we're a Manchester-based functional programming group, not a Scala-specific group, but more of a general purpose. We like lots of functional languages. We like computer science. We like all sorts of things. And yeah, I think that's really about it. So we've got Nicholas, who you can see at the side, and he's going to be talking about DSLs. We're going to get straight into it in just a moment. But yeah, there'll be, if you want to ask questions, just ask them during the talk in the YouTube chat, and we'll pull them in as we're going. And then at the end, I'll post a link to our Discord if you want to come and join us there. So yeah, let's get straight to it. Cool. I'll pull the slides in. Yep. Are you ready?
I am.
Absolutely. Go for it.
All right. Good evening, everybody. My name is Nicolas Rinedo. I work for a Swedish company called Becedo, where we do a lot of online content moderation and machine learning. And this has given me ample opportunity to mess things up in production in creative ways, which has in turn allowed me to build a really very long list about ways how to not do things, and a much shorter one about how to actually do things that works. And tonight I'm here because I'd like to talk about one of these things, domain-specific languages. Because, well, for two reasons mostly. First, I believe domain-specific languages are really useful and really neat, and people should do them a little more than do at the moment. And also because the encodings we have, the tools that we use in order to work with DSLs, involve a lot of concepts that are applicable to a lot of different problems. And I think people should know more about them. It would be helpful for people to know about them, and I like to talk about helpful things. So here we are. So the promise of this talk is, by the end of it, if you don't yet know what that is, you will know what a domain-specific language is, hopefully. I will also be talking about two specific encodings for domain-specific languages, generalized algebraic data types and tagless final. And you should understand what they are, how they work, how they compare, what trade-off picking one over the other involves. And finally, across the course of this talk, we are going to encounter most of the problems that you're likely to have to deal with when you write your own DSL, and how to solve them. What I will not even attempt to explain is what tagless final means, because I've tried to look it up and nobody seems to really know, so we'll just call it tagless final and assume it came from somewhere. Right, so if that sounds interesting to you, we're going to get started with one last bit of exposition in order to have some sort of coherent story to tell you throughout the presentation. I'm going to use a real world example from my job, actually, where we wrote a domain-specific language called Blang for Belang, Becedo language. Clearly, I was not part of the committee that came up with that name, but aside from the name, it's a great language that works, and that's handled on multiple millions of documents a day, and that's proven really helpful. So I'm going to use that, and I'm going to tell you a story about how it came to be, what problems we had, and how we solved them. And of course, since I'm using a real-life story to explain complicated stuff, it's going to be mostly, but crucially, not entirely fictional. Right, so, as I said, at Becedo we're doing content moderation. And the way content moderation works, or at least worked before I joined the company years ago, was we got a submission from a customer, and this submission, which contained a lot of information to moderate, was taken through an enrichment process in which meta-information such as geolocation information, ratio, vowel to consonant ratio, things like that. And all this meta-information plus initial submission yield what we call a document. A document which is then enqueued for an agent, which is just a fancy name for our moderator, for an agent to look at and either accept or reject. Now, that process worked really well up until the moment we got our first customer. And then we realized that the human capacity for creating offensive content far outstrips our capacity to try and spot it. Sorry. And so really quickly we found that it was too much work to do, and we, in order to try and solve the problem, we looked at the way agents worked, and we found out that in order to cope with the amount of offensive content they had to deal with, they came up with simple heuristics, such as if a document has a given category and a certain price, then we know for a fact it's scam. We're not even going to look at it, we're just going to reject it. So all these rules were very interesting because they could automate part of the process, and we decided to try and ask the agents to explain what rule they had so that we could implement them in the platform and automate that work for them. Of course, that didn't go down really well because agents, expert in their domain, which is moderation, and us, expert in ours, which is software development, don't really share a vocabulary. We have lots of words that they don't know. They have lots of words that we don't. And even worse, we have vocabulary that we think is in common, but doesn't actually mean quite the same thing. So when they told us what to do, we implemented what we thought they said, but it was always subtly different. And more often than not, what we implemented was not quite what they had in mind, which was frustrating for both members of that conversation. So we decided to have a sit with the agents, and we designed a formalized way of communicating words and instructions that we could use that was precisely defined, and in that way the agents would be able to communicate to us exactly what it was that we were meant to do. And well, that worked for a while because the agents would write down the instructions and we would quickly implement them. But the thing is, though, however quickly we implemented them, the data kept mutating because not only are human beings very creative when it comes to creating offensive content, but we also are incredibly efficient at understanding the rules that are put in place to stop us and circumventing them. So it really quickly became a game of cat and mouse where the offensive content creators would work out what we were doing to stop them and mutate the offensive content in some way. And then the agents would spot it and give us new rules. And as a developer, there's nothing quite as frustrating as trying to hit a moving target when you're implementing something and you know for a fact that within a week or two, you're going to have to tweak it again because, well, it's not working anymore because the data has adapted to it. And at this point, somebody, clearly, the way I'm presenting this, I want you to believe I invented that. I came up with that notion, but clearly I did not. But so somebody thought, we have a formalized language with formalized instructions, a set of vocabulary that we can use in order to communicate the intent of what the agents want to do. That sounds a lot like a programming language. A programming language, not a generic one, certainly, not something that you can use to solve any problem, but one that is very specific and very well suited for one specific domain, moderation, a domain-specific language, if you will. And that person said, well, we have been trying to compile these instructions and turn them into code to run in production, but we're not very efficient, we're not very good at it. Do you know what is actually very efficient at compiling stuff? A compiler. So how about we wrote a compiler that was able to take these expressions in that syntax that we designed and turn them into code automatically that we could execute in production, takes the developers entirely out of the equation and leaves the experts to write their rules and a system to interpret it. We did that, and that turned out to be extraordinarily successful and is still to this day running hundreds and hundreds and hundreds of documents and has been really very helpful to the entire moderation process. Now, the way this works is, at this point in the process, before we take a document and then queue it for agents to review, we inserted a bunch of rules that the agents we're able to edit, create, and delete. And the output of these rules, once evaluated on a document, were then sent for an orchestrator who would decide what to do with the document, either accept it, reject it, or, if unsure, enqueue it for an agent to pick up, and the rest of the process would stay the same. So all that introduction was to give you an idea of what a domain-specific language is and why it can be useful and how it can allow us to not actually have any work to do, which is pretty neat. But what we're really going to focus on is strictly that part of the process, the rules themselves, where a rule is something where you take a document, which is really a mapping from variable to number, and you apply a rule to it, and a rule looks something like that, where we can look for a specific category and a specific price, and then take a decision, true or false, depending on whether or not the rule has matched. Now, for the rest of this talk, we are going to take a much simplified version of the Blang language. We really are only going to handle what this expression down there needs to handle. Clearly, the actual language is a lot more powerful than that. It's got a lot more features, a lot more types. We even implemented regular expressions matching in there, and anybody who's ever tried to run user-generated regular expressions on user-generated content know how great an idea that turned out to be. But this is an expression. This is how we're going to handle it in this talk. And it's composed of the AND operator, Boolean AND, so true and false, etc., who has two operands, left-hand side and right-hand side, which in this expression both happen to be equals, which is numeric equality, compares two numbers. And this also takes left-hand side, here a variable, which is just a pointer to a value in a document, or a constant, a number literal. And this is what we're going to work with. Logical AND, numeric equality, variables, and numbers. And this is the entirety of a DSL. Right. Now, the first naive encoding, which should be your first reflex, because this really is the best way of encoding these things, is to write that as, well, a data type, which I'm going to call an algebraic data type. I'll explain what that is in a second, which in Scala is done this way. We create a type rule, and then we provide cases for all of the possible, cases of our DSL. For example, numbers. How do we present numbers? Well, we don't have much information about numbers aside from the number itself, right? So we just create a wrapper for that number that we'll call num, which allows us to represent all the numbers in our rule, and then we need to focus on the variables. Now, a variable is just a name of the variable in a document from which we're going to pull a number. So all we need to know about it is the string that it wraps, the name. And that tells us how to encode variables. And now, slightly more complicated, we have the operators, equals, which, given a left-hand side and a right-hand side, which both must be rules as well, we'll compare them for equality. So we need a left-hand side and a right-hand side, which we stick into a case which we call EQ. And this tells us how to represent equality. And finally, AND, which also has a left-hand side and a right-hand side. So it behaves exactly the same way as AND, a wrapper for left-hand side and right-hand side that happens to both be rules. Now, this is what we call an algebraic data type, or an ADT for short. And the important things to know about algebraic data types are, this is a topic on which I could talk about at length and have indeed done quite a few times in the past. So I'm going to give you a real short definition here. Sorry, I skipped ahead a little bit. An algebraic data type is a type that is composed of a known set of possible alternatives. So here we have AND, EQ, var, or num. And you can think of it as an OR between all of these types. A rule is an AND, or an EQ, or a var, etc. Each of these branches, each of these cases, is composed of a known number of values. So n, for example, is composed of two values, the left-hand side and the right-hand side. And var is composed of a single value, the name of the variable that it points to. And finally, an important aspect of algebraic data types. If you look at rule here, a rule can be an EQ, which contains a rule. rule is defined in terms of itself. It's a recursive data type. So that gives us a definition, a useful definition of algebraic data types. They're potentially recursive subtypes of product types. I realize now that I forgot to define product types. If we go back a few slides, and is composed of two values, left-hand side and a right-hand side. And you can think of that as an and between type. It's a left-hand side and a right-hand side, and that is known as a product type. Sorry about that. Right, so that's our algebraic data type encoding. And we can even create values of it. And if you look at the values, it makes it very apparent, even at the value level, that this is a tree-like structure, because we have the root of the tree, the intermediate nodes, and the leaves. Now, one problem that I have with that is that when you create a value of type rule, it looks nothing like the syntax we defined earlier with the dollars and everything. And I find it kind of hard to reason about it when I have different ways of looking at it that are equivalent but don't look remotely the same. So what we usually do at this stage is provide syntax for a DSL, which in Scala is a little bit noisy, but makes things a lot more pleasant, so is worth the effort. This defines an equals operator, which given the left-hand side and right-hand side, wraps them in a rule.eq. And similarly, and, given the left-hand side and the right-hand side, wraps them in a rule.and, which allows us to simplify our rule by replacing eq by the equals operator and end with the and operator. But these bits here are still a little bit unpleasant. We're not going to be able to get exactly what we had with a dollar or with the row numbers, because that would likely involve some sort of implicit conversion, and sane people don't do implicit conversion, so we're not going to do that. But we can at least make things somewhat better by using lifting operators. Num here, which given an int, lifts it into a rule.num, and var, which given a string, the name of a variable, lifts it in a var. Right. So, having that, we can now update our rule to look a lot more pleasant to read. So I'm happy with that. This looks nice. This looks readable. I understand what it says. But when you print it out, when you evaluate it, back to the mess. And this is something that you're going to see a lot of, because when you debug your implementation of your DSL, you're going to print out expressions quite a bit, and this is not helpful. So the very first thing we're going to do is we're going to write a pretty printer for that DSL with a pretty function that, given a rule, returns a string representation. Now, as we've seen, an algebraic data type is a recursive data structure, and in order to process recursive data structure, your first reflex should always be to use natural recursion or structural recursion. I believe the two mean the same thing. So this is what we're going to do here. How would we represent numbers? Well, really, we just want the string representation of the number and nothing fancier than that. So this is what we're going to implement. If we encounter a number, its string representation is just that, is string representation. Variables are a little bit fancier because we have to prepend that $sign. So when we encounter a var, we represent it with $ followed by the name of the variable. And equality, numeric equality, is going to print out the pretty printed version of the left-hand side, followed by equals, followed by the pretty printed version of the right-hand side, which in terms of code looks something like that. Pretty printed version of the left-hand side, followed by equals, followed by the right-hand side pretty printed. And finally and, which works exactly the same way. We have the left-hand side, the right-hand side. We pretty print the whole thing. Pretty print the left-hand side, followed by and, followed by the pretty printed version of the right-hand side. And in terms of code, we're basically doing the same thing as EQ, except we're using and instead of equals. And if you were to now try and pretty print the rule we defined earlier, it's going to yield exactly what we expect. So that's nice. We've done a first very basic interpreter, and we have learned a few things. So what have we learned so far? We have learned that algebraic data types are potentially recursive subtypes of product types. It's a useful definition to have, so keep that in your head. We have learned that DSLs are very easily encoded as algebraic data types, and that so far interpretation is really just natural recursion. Now, at this point, I'm going to start going a little deeper into the material. So if there are things that are not clear so far, it would be a good idea to ask them now. And if not, I can just carry on.
I'll pull one question in that we've had,
Sure.
which is this one here. Didn't know Scala had infix operators. I suppose that's a bit like Haskell's backticks, but you pre-declare them. Yeah, Scala does. You're using Scala 3 as well, aren't you?
Oh, right. Yes. Did I not mention that? Sorry. Yes.
Yes.
This is entirely done using Scala 3, which has a lot fancier syntax that you'll find looks a lot more like an ML language because we don't need the curly braces. We can use significant white space. We have infix operators. It's not quite OCaml or its beautiful syntax, but it's a lot more pleasant.
Yeah, absolutely. But yeah, so Scala 2 and 3 does have infix operators, but they are significantly better in Scala 3. That much is definitely apparent. Well, we'll give it another 20 seconds if anyone wants to ask a question, and then we'll carry on onwards. But thought that was worth clarifying.
Cool.
But yeah, absolutely. I think no more questions. All right, we're gonna keep motoring. If more come up, we'll pull them in as we go along. But
absolutely.
Let's keep going.
Cool. All right. So now that we have implemented our first interpreter, pretty-printing, well, that one is useful. It's going to allow us to debug stuff. But it's not really what we set out to do, is it? What we really want to do is to compile these rules so that they can be evaluated in production against real documents. So this is what we're going to be doing now. Now, what's a rule? Well, we've seen a rule is a mapping from a document to either true or false. And we're going to need to put types on that. So true or false is pretty easy. That's a Boolean, right? But documents, we haven't defined a type for that yet. But as I said earlier, a document really is just a map that maps a variable name to a value. So we're really just going to say it's a map from string to int and alias that to the type doc. And what we want to compile our rules to is a function from a document to whatever that document evaluates to, some code that looks like that. And we're going to do exactly the same thing we did for pretty-printing. We're going to write a compile function that, given a rule, returns a doc to Boolean function, and we're going to do it through natural recursion. So again, let's start with numbers. Well, a number is a constant, isn't it? So regardless of what document we're passed, we're going to return that constant. So if we encounter a number, we just ignore the document and return the number's value. But that fails to compile because, well, the value is an integer, isn't it? We said. But we also said that our rules were functions from document to Boolean. Well, it's a sign that something is kind of fishy with our implementation, but we're going to try to sneak a quick fix in, see how far we can get. Clearly, we're not going to get all the way through because there's something flawed in what we've done, but we're going to go as far as possible to really understand what the problem is. And in Scala 3, we have union types. So we can say, well, actually, we're not returning a Boolean. We're sometimes returning an int, sometimes returning a Boolean. You work it out, and the compiler does. And now it's happy with this implementation. Bit of a hack, but it's going to allow us to learn more about the problem. Right. So how would we present variables? Well, we're just going to look the variable name that we have inside of the document, right? So we'll do something like that. Given a document, we are going to look the name up in a document. And yes, that is perfectly unsafe code. If the name of the variable is not defined in a document, not sure whether it's going to throw an exception or return null, it's going to do something nasty anyway. We could easily do error handling, but it would not be useful for this talk. It would make the code harder to follow. It would not be the point it would not help the point I'm trying to make. So within the context of this talk, we're going to say, well, it's absolutely fine if we're trying to access a variable that doesn't exist. It throws an exception that's going to be caught by whatever is running these things and handle that as, well, the rule hasn't matched and log an error. So try not to focus too much on the fact that some of this code is not unsound, but unsafe. Right, so this works. And now equality. Equality, well, we're going to look at the left-hand side, look at the right-hand side, and compare them for equality, right? Which in terms of code is going to look something like that. Compile the left-hand side, compile the right-hand side, and then given a document, We evaluate the left-hand side on it, the right-hand side on it, and we compare them for equality. But that, again, doesn't compile. Because in Scala 3, for whatever reason, you cannot compare an int and a Boolean, an int or a Boolean with an int or a Boolean. A little bit frustrating because it seems pretty easy to write that, isn't it? If you have two ints, you compare the ints. If you have two Booleans, you compare the Booleans. Otherwise, they're not equal. But Scala doesn't actually support that. And in this instance, it's actually very useful because I've been very careful to mention multiple times that equality was numeric equality. It was not any equality. It was definitely not universal equality. We're not comparing anything with anything. We're comparing numbers with numbers. And here we end up in a situation when we get to compare Booleans with Booleans and maybe Booleans with ints. It's precisely not what we wanted to do. What we could do, but we're not. But what we could do is say, well, let's change the specification because what we are actually asked to do is a little bit complicated, so let's change the specification to make it easier for us. That's usually not a good sign when you start reasoning that way. So what we're going to try to do instead is fix the problem and make it so that EQ is strictly numeric equality as specified. And the problem we have is that rule, sorry, we'll get to that just a bit later. Rule does not encode in any way what kind of variable it contains. And we know that numbers and variables contain integers, and EQ and AND contain Booleans. When I say contain, that's a very loose definition of contain, but an EQ is eventually going to evaluate to a Boolean, and a num is eventually going to evaluate to an int. But our rule does not encode this information. So in order to encode that, we're going to add a type parameter to rule, a, which tells us what this specific rule will evaluate to. So numbers are rules of int, because they're going to evaluate to numbers, to ints. Variables also evaluate to ints. EQ, on the other hand, evaluates to a Boolean, but we also need to fix its parameter. And we know that EQ must be a numeric equality, right? So the left-hand side and right-hand side must both be rule of int. Similarly for AND, it's a rule of Boolean, whose left-hand side and right-hand side are rules of Boolean. And that is an improved encoding, and this is called, nope, sorry, a little bit more code to go through first. We are going to need to update the syntax. Equals doesn't take rules, but rules of int, and AND doesn't take rules, but rules of Boolean. Right, and that's all fixed. And now, this encoding is known as a generalized algebraic data type. I'm not sure what's so generalized about it. I never really understood that name. And I'm going to give you a simplified definition here, because we don't need the entire power of generalized algebraic data types. Here, what turns this algebraic data type in a generalized algebraic data type is A, the type parameter, which we call a witness type when we talk about generalized algebraic data types. I'm going to say GADTs from now on because it's a mouthful. So when you talk about GADTs, A is a witness type. It's used to encode a specific information about the various branches of the sum type. Here, we are encoding the type to which the branch is going to evaluate to when evaluated. And this witness type has interesting properties. It carries type information that can be compared for equality, and that allows us to refine pattern matches and do clever things during pattern matches. We're not really going to see that here, or kind of under the hood, but we're not going to focus on that. But this is what the GADT is for the purpose of this talk. Right, so now we need to fix compile, which rule needs to take a type parameter. So we need to take a rule of A, which forces us to define type parameter to compile. And that A, well, we just define that as the value our rule, the type our rule was going to evaluate to, right? So we know that we don't have a function from doc to int or Boolean anymore. We know by the type that it's got to be a function from document to A. And having done that, this will compile because the left-hand side is a rule of int, the right-hand side is a rule of int. So when we evaluate them, we get integers, which we can compare for equality. And finally, AND, which works similarly, evaluates the left-hand side and the right-hand side and compare them with the logical AND, which yields code that is almost the same as for EQ, except we're using AND and not equal to compare them. That all works out, and if we compile the rule that we defined, remember the one that looks for category ID 10 and price free, I believe, then we evaluate that against a document with category ID 10 and price free. Then that evaluates to true, but if we were to change category ID to 11, then that evaluates to false. Now, that's not a good enough test. If I were to do some code review and see this kind of test, I would not be happy. This is not sufficient. But for the purpose of this talk, it should give us a good intuition that things are working the way they should. Right. What have we learned so far? Well, we have learned that algebraic data types, ADTs, aren't sufficient. Sometimes we need GADTs because they allow us to encode type constraints that ADTs just can't. And finally, GADTs do not make interpretation any harder. Actually, we could recompile the printer from before without needing to change anything whatsoever. It would just work. So, well, before I get into other interpreters that we have to implement when we handle the DSL, do we have questions at this stage?
Don't think there's anything in the YouTube chat right now. I'll give everyone a moment. But yeah, I think that was a
pretty clear then. Okay.
Yeah.
Great.
I think so.
Let me keep going then.
Yeah, let's keep going.
Right. Another problem that you're likely to encounter, well, it's really nice to have rules that you can evaluate, but you need to be able to store them and pass them on the line. You need, for example, to have a web form in which your agents will write the DSL and send that over to your server for you to store, compile, and evaluate. So we are going to need at some point to serialize and deserialize them. The serialization process is a process of taking a rule and serializing it to a binary, not a binary, a format, which here happens to be JSON. Now I could have picked any format but JSON, but I picked JSON for two reasons. A, most people understand and know JSON, and those who don't can probably read it within 5 seconds because it's so clear. And B, everybody in the Scala community has at some point implemented a JSON library, and I have not so far. So this gave me the opportunity to do so for this talk, and it was lots of fun. So we're serializing to JSON, and within the context of my library, serialization is done by a type called encoder. So given an encoder for rule of A, we can encode a rule of A to JSON. And if that is provided, then our type is enriched with an asJSON method, which encodes our rule to a JSON object. And once we're done with serialization, we have to deserialize, which is the opposite process. We go from a JSON object and turn it into a rule with a little bit of error handling on top, because not all JSON documents are legal rules, but it's basically a function from JSON to rule. And that is handled by the decoder type class, which works similarly. Given a decoder of rule of A, then I'm capable of taking a JSON and turning it into a rule. But what that enriches the JSON object with an add method, which, given the right type, does the right thing. So as rule of A is going to turn it into a rule of A. Now the thing is, we're never going to want to decode JSON as a rule of A, because that's not very helpful. We don't know what A is. What we're going to want to decode it as is either a rule of int for numbers and variables, or a rule of Boolean for and equals. So what we're actually going to need to provide is two decoders, one for rule of int and one for rule of Boolean, because these are the only types that we know how to decode to. Rule of string, for example, would not make any sense. Right, so let's do them sequentially, because encoder and decoder being two sides of the same coin, it's clearer to do them at the same time. How would we encode number in our DSL? Well, JSON has number types, so we could just encode a rule number to a JSON number. So if we encounter a rule number, we just turn that into a JSON number. And the decoding part is just the opposite. If we encounter a JSON number, we turn that into a rule number. Category ID is just, a variable is just a string, so we can encode that as a JSON string. If we encounter a variable, we turn that into a JSON string, and vice versa. If we encounter a JSON string, we encode it as a variable. And those are the only two possible instances of rule of int, because the only other two options that we have are and equals, which are rule of Boolean. So we're done with rule of int, and if we were to encounter any other JSON at this point, we know it's an error. So we can just return an error. Right. Now, the operators, EQ. Well, we're going to say that EQ is encoded as a JSON object with a single key equals that maps to an array with exactly two elements, the left-hand side and the right-hand side. And that is just what we're doing here in terms of code. If we have EQ, where we turn that into a JSON object with a single key equals that maps to a JSON array with the left-hand side and the right-hand side. And the decoding process is going to be the same. If we find that structure, then we're going to decode the left-hand side as a rule of int, decode the right-hand side as a rule of int, and wrap the result into a rule.eq. And end behaves exactly the same way with a single key called end that maps to an array with the left-hand side and the right-hand side. In terms of code, we have exactly the same thing as for EQ, except the key is end and not equals. And the decoding is going to behave the same as well, except for the fact that we're decoding to rule of Boolean, not rule of int, and that we're wrapping in an end. And again, EQ and end are the only two possible rule of Boolean. So if we encounter any other JSON, we know it's an error, so we can just return an error. And now that we have done the entire chain, we can test things out. Given our rule, we can easily encode it to JSON, and it yields exactly what we wanted to see. And for the decoding, we're going to go for the round-trip property, which says, well, given a rule, if we encode it to JSON and then decode it back to rule, then we should get exactly what we started with, which we do. So that actually is the end of Theorization Deserialization, which is fairly straightforward when you do ADTs. What have we learned? Well, we have learned that theorization and deserialization are relatively straightforward. Theorization is just another interpreter, and deserialization does require a little bit of manual work, but it's not much more complicated. Again, if you have any question, now is a good time to ask them before I move on to the next part.
Well, there was one question, but I think we'll leave it to the end because it's kind of more of a wrapping up type question. Someone said this, which is everyone has written a JSON parser, which is pretty true. I've been sensible enough to not do that and just pull in Circe in the past, but like
I'll give it a shot. It's really fun.
Yeah, no, probably is a thing I should try at some point. Absolutely. Let's see. We'll give it a moment more for any other questions, and then we'll keep on motoring. It's quite nice to see the given syntax as well. I've not really had a chance to do any Scala 3, so
I'm actually trying really very hard not to bring any attention to that.
Yeah.
Because
fair enough.
no, but I understand that at least a large chunk of the audience doesn't know Scala and is probably not terribly interested in. So yeah, we're using Scala free syntax, but I'm trying to highlight the relevant bits and not necessarily the entire syntax.
No, that's fair. Absolutely.
Right. So no questions then so far.
Yeah, no questions right now. Let's keep going. If we'll pull anyone's in as we get towards the end of it, but yeah, sounds good.
Works for me. Right, and the final thing that you might have to do when you work with DSLs is you might have to transform them. Now, why would you have to do that? Well, take a look at this rule, which looks very much like the one we've had so far, except for that bit, 1 equals 1. And if you're anything like me, you want to change that. You want to say, well, that's not good. I want that to read true. But we can't, because we don't have the vocabulary in our DSL to express raw Booleans. So, well, we don't really have much of a choice. If we want to optimize our rule, if we want to turn numeric comparison where we know both operands to the actual Boolean that they map to, then we're going to need to extend our DSL. We're going to need to have to add a type for bool. And then we're going to have to fix everything. We're going to have to create syntax for bool. We're going to have to fix the printer to handle the bool case. We're going to have to fix the evaluator to handle the bool case. We're going to have to fix the JSON encoder. We're going to have to fix the JSON decoder. And finally, once we've done all that, we can write our rule simplifier, which is a simplify function, which given a rule, returns a rule that we hope is simplified. Might not be, because it might not be simplifiable, but at least it's going to try and return a canonical version of the rule. Now, how would that work? Well, it's an interesting case here. If we encounter an equal statement that compares two row numbers, two constants, then we're going to want to remove the entire thing and replace it with a corresponding Boolean. So in terms of code, that looks fairly straightforward. You can just say that. Sorry, if we encounter EQ of two nums, then we replace the entire thing with a Boolean whose value is the left-hand side, whether or not the left-hand side is equal to the right-hand side. Now, end doesn't really need to be simplified, but end contains rules, and if we don't simplify the right-hand side here, we're never going to get to simplify our EQ statement. So we must not forget, when we have recursive data structures, to simplify recursively. So if we encounter an end, we must simplify both the left and the right-hand side. Similarly, EQ has a left-hand side and right-hand side, which are both rules, so we must not forget to simplify this either. And anything else are final terminals of our language. They cannot be simplified further because they are as simplified as they're going to get. So we just leave these alone. And now, if we take our complex rule, which is only complex in that it has this 1 equals 1 statement, which our previous example did not. And if you take this complex rule and run it through our simplification process, then we get exactly what we wanted. And what have we learned there? Well, we have learned that statement transformation is just a regular interpreter, if your language is rich enough to support it. If it's not, though, then you can be in a little bit of trouble, because language modification is unpleasant. It wasn't pleasant for us, because we had to go and fix all of our interpreters. But when we did that with Blang, well, we fixed all the problems. We fixed all the resulting non-exhaustive pattern matches. Took a couple of days of work, but everything was fine. And then I started receiving lots of really angry phone calls and emails, because what the thing is, when you write something useful, surprisingly, people will start using it. And in our case, first, the backend team thought Blang was neat, because they realized that evaluating a Blang rule on one document or on hundreds of thousands of documents was not very different, and that you could compile these rules to a SQL statement. That turned Blang into syntax for a search engine. And we broke that because all of a sudden we had new syntax that they had not handled and nothing compiled anymore. We got angry emails from QA because, well, they'd realized that, you know how you write a test. Given this input, I take it through this process and I expect the output to look something like that. Was discovered that I want the output document to look something like that was very conveniently expressed using this DSL. So they started using that, and we broke all the tests. Got an angry email from front end because they'd made exactly the same realization as the back end. Blang is brilliant syntax for a search engine, so they implemented that in the browser to turn that into Elasticsearch queries so that customers could search for whatever documents they wanted in our UI. And finally, a bit more mysteriously, I got an angry phone call with the head of the DevOps team who had implemented something that compiled Blang to Kubernetes YAML. Now, I'm not even sure what that means, and I did not want to get into that story, but yeah, he was upset too. So yeah, language modification can be unpleasant and can have expensive ramifications. Now, what have we learned?
Oh, yep. I was going to say there's a couple of questions I was going to pull in as we're at the key takeaways. So
all right,
one of them was simplifying and when one of the other operands is a Boolean, and then it mentions the Boolean constant, which I think
we could absolutely do that. I leave that exercise to the viewer. It's definitely something we could do. We could plug it into the same simplify expression, or we could write another simplifier and chain them. Definitely, absolutely, yes.
Absolutely.
I have already shown you how to do it with Zen, so I thought maybe doing it twice would be a little redundant for the talk, but absolutely you should do it.
And then this question here, is simplifying really a form of evaluation? Which, yeah, I'd say...
It is.
Yeah.
I mean, evaluation is, well... Do you mean evaluate? Well, it's a form of interpretation, really, because interpreting a DSL is turning your DSL from a DSL statement into something else. And here, this something else happens to be another expression of the DSL, but it's still interpretation, right?
Mm-hmm. Yeah, exactly. That's basically what someone else said. So hold on. Yeah, there we go. You're evaluating another version. Yeah, this is sort of responding to that question. But yeah, that absolutely is the case. Cool. I don't think there's any other questions. I thought we'd pull
All
some
right.
up. We got to
So
here. Yeah.
let me give you quick conclusions about general algebraic data types, and then we'll move
Yeah.
on to something else.
Cool. Sounds good.
So with JDTs, adding an interpreter to a language is very easy. It's just writing a new function and usually writing it using structural recursion. But adding statements to a language is hard. As we've seen, we had to modify everything. Every single interpreter, every single bit of syntax we wrote needed to be modified. And that happens to be known as the expression problem, at least a specific case of it. The expression problem is an interesting problem that Philip Wadler came up with a while ago now, which paraphrased and adapted to fit this presentation states something like, the problem is to try and write a DSL in such a way that adding interpreters and statements should be doable without having to recompile anything. You have to compile the new stuff that you wrote, of course, but you do not have to recompile any of the things you wrote before. And generalized algebraic data types cannot solve the expression problem, at least not the way we've done it here, because we've seen that we need to recompile and modify and recompile every single one of our interpreters. And the reason for that is generalized algebraic data types, JDTs, are data, and data doesn't really compose all that well. And what we want to do is we want to be able to compose our statements. So we want to say, well, I have this Boolean operator, this bool syntax. I have this and, EQ, num, and var syntax, and I want to be able to compose them to create a new DSL. And we can't do that with JDT. But what we're going to try to do here is create a composable encoding. And the intuition we're going to follow is, while data doesn't really compose, something else famously does. Functions. Functions do compose. They're famous for it. So let's try to see how far we can get by trying to encode our DSL as functions. So again, this is our DSL, and we're going to run through the same process, but with a completely different encoding now. This is our DSL, and how would we encode 10 and 3? How would we encode numbers as functions? Well, we could do that. We could create a num function, which takes an int and return this string representation. Similarly, this tells us how to encode numbers. Similarly, variables, well, we'd encode them as a variable function, which gives given a name, return the string representation. And that tells us how to represent variables. Equals, as we've seen before, we could just call it equal. I would have called it equals, but Scala runs on the JVM, and equals is kind of a reserved keyword, or well, you can use it, but it's going to end up doing weird things. So I have to call it equal here. And so equal takes left-hand side and right-hand side and pretty-prints it. And finally, end works the same way. The end function, which given the left-hand side and right-hand side, pretty-prints it. Right. This encoding, this looks like it works, but it has a few flaws. The first one is we're being a little bit rude because we're declaring these functions with very common names in the global namespace, which is that anybody that uses our DSL cannot use num, variable, equal, and end. This is kind of rude, it's bad practice. So what we're going to do is we're going to stick them in our own namespace so that people can happily keep using their own code and thus just import our namespace when they need to. Sorry about that. There we go. I skipped ahead quite a bit, so sorry. The rule value in which the tree-like structure is apparent as before because we have the root, the intermediate nodes, and the leaves. And now these functions which we want to stick in our own namespace, which we're going to call rule. In Scala, you open and close namespace with package, package object, or objects like here. Now, this allows us to modify our rule value. Well, first, I'm going to do a little bit of moving things around. And now, I can just import everything that is a rule object, and everything is going to compile as it did before. And if we evaluate that rule, we get what we expect, right? It's a pretty rendered version of the rule. But is it what we were hoping for? I mean, certainly we will want to write a pretty printer at some point, but that's not the only thing we want to write, is it? I mean, really, what we want to write is at least a compiler and evaluator, right? So there's a problem here, and the way we're going to fix it is, first we're going to realize that the problem lies in the fact that all other functions return a string. We don't necessarily want them to return a string. The pretty printer should return a string, but the compiler should return some sort of function from documents to a or int or boolean, right? So we're going to want to replace that string. We want to say, well, a rule has a type parameter which represents the type it's going to evaluate to. So we don't have string anymore. We have a, and objects in Scala cannot have type parameters. So we're going to need to turn that into a trait, which, if you don't know what a trait is, it's basically a Java interface. It's a purely abstract class. Traits don't need default implementations, so we can get rid of the default implementation. And there we go. Now, we can't really import everything in rule because rule is not an namespace anymore. It's something we must take as a parameter. It's a value that we must get. Now, what I'm about to show you is going to look really scary because Scala syntax can get a little bit hairy. This is what we're going to do. I'm just about to explain that, and it's a lot less complicated than you think it is, and additionally, it's about to get much worse as well, so you have that to look forward to. But what this says is that rule now is a function that first takes a type parameter, a, and then a value parameter indexed on that type. It's a polymorphic function, and if you know what that is, it's brand new to the Scala language, and it's really cool. And then, having these two parameters, one type parameter and one value parameter, you evaluate the entire body. We don't really need rule here, because it's in R, right? We get a rule that we called R, so we import everything in there. And that's it. That's going to work. But that is going to work as well. Can you spot the problem? It's right here. We're taking the logical end of two integers, because num is an integer, right? So we have fallen in exactly the same trap as we did for JDTs. We lack some type information. The problem is here. We know that end takes two a's and is going to return an a, but we have no information about what kind of a we have. We don't encode the fact that it is an a that feels like a boolean or an a that feels like an int. And we're going to use exactly the same fix as we did for JDT to add more information at the type level. We're going to say that we're not taking an A, but an F. Now, that syntax just means F is a type constructor. It's not a type, it's a type constructor. It takes another type to build a type. Now, to give you a concrete example, list is not a type. List is a type constructor. List of int is a type. So when you pass int, the type, to list, the type constructor, you get the concrete type, list of int. This is what we're doing here. And now, we know that num is an f, both num and variable are f of int, because they return an f that is somehow indexed on int. Similarly, equal and and return f of boolean, because they both return booleans. And they equal takes f of int, because it's numeric equality, and takes f of boolean, because it's logical and. Having done that, we need to fix our bad rule, because we now take f as a type constructor instead of the type a, and that now fails to compile. Because it's saying, I'm expecting an f of boolean, I'm expecting something that feels like a boolean, and I'm getting something that feels like an int, that's not going to compile. So it's exactly what we wanted, and luckily, our good rule still compiles, because once we fix it so that we have an f and not an a, everything works just fine. There's one last problem with this implementation. Well, first, we haven't given it the right name. There's two problems, I guess. I forgot about one. Now, in functional programming, we do enjoy giving absolutely horrible names to very simple things. This is no exception. If you read the original paper on Tagless Final, this is called a semantic. It's not a problem with my French accent. I didn't mean to say semantic, semantic, for Movalis between syntax and semantic. Because rule, here, describes the syntax of our DSL. It gives the operators and the terminals, num, variable, equal, and end. And values of type rule give us the semantic of this specific interpreter, because it tells us how to actually run the interpreter. So we have something that is both syntax and semantic. We're going to call it a semantic. And traditionally, that means we call anything that is a semantic sim. So this is rule sim. And once we fix rule to take a rule sim, we're pretty much done, except for the fact that this looks nothing like the expressions we initially wrote. We're going to need to add some syntactic sugar, which is easily done. Here, we have defined the equals operator, which given a left-hand side and a right-hand side, calls the equal method on both. Similarly, end, which given a left-hand side and right-hand side, calls the end method on both. And we're also going to need to write operators to lift row numbers or row strings into our language. Num, which given an int and a rule sim, will call num from that rule sim onto that value, and var, which given a name of a variable and a rule sim, calls a variable method. Having done all that, we can now simplify our expression. Well, last bit of syntax, we're using extension methods on given instances. Don't really need to understand what that means. It just means something in here is implicit. And when you want to use implicits, you have to turn that arrow into that weird symbol, which only means whatever comes before the question mark is implicit. So here, we have marked our rule sim as implicit, which allows us to replace variable and num by the corresponding operators, equal with the equals operator, and end with the end operator. And given that this was given to us implicitly, everything is already in scope. We don't actually need an import statement. And finally, we don't even need to give a name to our rule sim because we're not referring it by name. We just need a value of that rule sim, but we don't care how we call it. So we can just say anonymous. And that is how we would encode our rule, which, if we try to print it, gives this absolutely horrible printed version. And I hope the Scala team fixes that in the compiler. Just as an aside, this presentation, the Tagless final part, heavily relies on polymorphic context functions, which means polymorphic functions with implicit parameters. And the paint is not completely dry on that in the compiler. A few things have not been properly implemented yet. They're working on it. So this is a little bit bleeding edge, but I think it still manages to work for the purposes of this presentation. But so this is a horrible type, polyfunction of blah. We're not going to use that. We're going to call that rule, because we're not very creative with names. And the rule of A is exactly what we just defined, a polymorphic function, which, given a type constructor f, and a rule sim for that f, returns an f of A. Let's put some concrete types on that, because this is all very abstract here. Let's write our pretty printer. Now, writing an interpreter in this encoding involves providing a rule sim of the type we're looking for. Pretty printer turns a rule into a string, so we're going to write a rule sim of string. And then the implementation is the one that we've already seen a bunch of times before. We don't need to go through that again. But of course, if we try to compile that, that's going to fail to compile. Because, well, we said that semantics, rule sim, took a type constructor, and string is not a type constructor, is it? It's a concrete type. Now, in order to fix that, we can use this simple trick. We can declare a new type, pretty, which is indexed on the type A, which will completely ignore whatever A, pretty of A, is a string. So at the value level, it doesn't actually change anything, but at the type level, information that will be lost at compile time, this tells the compiler, this gives the compiler the context it needs in order to make sure that we are combining strings that are actually kind of int with strings that are kind of int and not with strings that are kind of booleans. So if we replace rule sim of string by rule sim of pretty, and of course, for equal, we're not taking strings, but pretty of int, which maps to string. But at least here, we have the information that it's an int kind of string. And similarly for end, we don't take strings, we take pretty of booleans, which are strings again, but they're boolean-like kind of strings. And now this all works out. And when you try to evaluate rule as a pretty, so when you explicitly specify the type under which you would like to evaluate rule, this allows the compiler to work out whether or not it has a rule sim of pretty. It does, so it's going to evaluate the entire thing and pretty print it exactly the way you'd want to. And I think this syntax here is all kinds of brilliant, because its rule is a value, and you tell the compiler, well, this is a value, and I want to represent it as this kind of type. So it's not exactly a polymorphic value, but it feels very much like it, doesn't it? And I think this is kind of cool. Right, so what have we learned? We have learned that when encoding a DSL as function composition, we use a type class to describe its syntax and semantics. So the type class is ruleSim. RuleSim describes the syntax because it declares all the various operators that we have. And the semantics are in the actual values of type RuleSim. So for example, our pretty printer, which has an implementation of all of these operators and operators, and actually knows how to interpret them and what to do with them. So that's the semantics of your DSL, of your interpreter. We encode expressions of the DSL as polymorphic functions, and this is known as the tagless final encoding for reasons that are beyond the understanding of mere man, at least this mere man. And before I continue, is there any questions so far? I expect there to be a little bit more questions because this is a little bit more complicated than the DDT encoding.
Currently, no. Yeah.
So either I've lost absolutely everybody, or it's clearer than I thought it was.
Here we go. Here is a question which I shall pull in.
Right.
How does this solve the problem of adding new operations to your DSL, or is it solving a different problem? What's the benefit in the end over the GADT encoding?
I will be spending the next 15 to 20 minutes answering that question. That is the rest of the talk.
Well done on predicting where we're going.
Right.
Let's give everyone just a second more, because as you say, I think that was quite a complex part, especially with the polymorphic functions. But so you'll definitely get your answer, Timo.
All right. Well, in that case, I'll keep going and just ask questions later if you need them.
Let's keep.
So you know what we're doing now, right? We're doing the various interpreters we saw before, but as a tagless final encoding. And now that we have the encoding down, this is not so hard, because compilation we've seen is taking a document and evaluating it to either a Boolean or an int. So a compiled version of a rule is a function that goes from document to something. That something being either Boolean or int, depending on the rule that we're manipulating. So compiling a rule is done by providing a rule sim of functions of type doc2, and that syntax here means doc2 something. There's a type hole here. That's the type parameter of your type constructor. In the case of equal, it takes functions from document to int. In case of n, it takes function from document to Boolean, so that we still get the right types. We have numeric equality and Boolean end. How do we implement that? Well, as we've done before, actually, the same logic carries over from the GDT encoding. Numbers are encoded as just numbers by ignoring the document. Variables are just looking up the name of the variable in a document. So we get a document and we look up the name of the variable in the document. Equality is done by looking, as before, at the left. Given a document, we look at what the left-hand side evaluates to and what the right-hand side evaluates to, and we compare them for equality. And n is going to behave exactly the same way and have exactly the same code as equal, except we're now using and not equal for comparing operands. And having done that, we can just ask for a rule to be compiled as a function from doc to something, and we get compiled, which if we evaluate it to with the document that we're used to working with, we're going to get true as expected. And if we change the category idea to 11, then it's not going to match anymore, which is what we expected. Theorization Deserialization, which is just as straightforward. Now recall that theorization is taking a document and turning it into a JSON object through an encoder. And the encoder, as we said, is just an interpreter. So we're going to need to provide an interpreter for JSON documents, a rule sim of JSON. But as before, JSON is a type. It's not a type constructor. So it doesn't have that hole in which we can describe what kind of JSON document it represents, whether it's an int or a Boolean, right? So we're going to have to use the same trick, a JSON rule of A, which whatever the A is a JSON. So we're providing a rule sim of JSON rule with all the right types filled in. And then we're going to provide the implementation. But first, deserialization is the other way around. We're going to provide the two decoders, one for rule of int and one for rule of Boolean. And we know we're going to need a fall-through case, so I've already provided the error handler in case we didn't recognize the JSON that we got for input. Right. So how do you encode and decode numbers? As before, JSON numbers. So if you encounter a num call, you turn that into a JSON number. And if you encounter a JSON number, what you do, you have a little bit of boilerplate because you want to return a rule, right? And you know that a rule is a polymorphic function that takes a type parameter, f, and then a corresponding rule sim. So that's a little bit of boilerplate. And then you just call num on the corresponding rule sim. So you turn that into a number of your language, of the DSL. Similarly, for variables, when you encounter a DSL string, a DSL variable, you turn it into a JSON string. And if you encounter a JSON string, you turn it into a DSL variable. And that's the entirety of a decoder of rule of int, because we do not have any other operator that works on that returns int. So we're going to have to go for equal and end now. Equal, well, as before, it's a JSON object with a single key equals, etc., etc., etc. And the decoding was a little bit more wordy, but as before, we decode the left-hand side as a rule of int, the right-hand side as a rule of int, and then we stick the entire thing into a DSL equal statement. And end works the same way as equal. It's basically the same code for the encoder, except we have the end instead of equals. And the decoder is very similar, except we decode the left-hand side and right-hand side as Booleans. And we combine them using end and not equal. Now, that all works out. And having finished our rule sim, we can wrap it into an encoder, because if you recall, we need an encoder in order to be able to call the asJSON method. But the encoder is just a proxy to our interpreter. Now, rule.asJSON, so encoding our rule into a JSON expression, works exactly the way you'd hope. And the round-trip property holds as well, because given a rule, if you serialize it to JSON and then deserialize it back to a rule of Boolean, then you get exactly what you started with, which is exactly what we wanted. But I'm not very happy yet with this encoding, with this implementation, sorry. Because there's all this boilerplate, which, the good thing about this kind of code that some people tend to like is it looks really very smart, doesn't it? Whoever wrote that must be really good at computer sciences, because I don't understand that. And I wrote that, and when I read that, I still have to focus, try to work out what the hell does that mean. But I think this is a sign of really bad code. Good code should be code that people don't have to struggle to read. Good code should go the extra mile, which actually takes a lot of work, but should go the extra mile of making it simple. The reaction that good code should provoke is not, ooh, whoever wrote that is really smart, but, well, obviously, how else would you implement that? So that's what we're going to try to do here. We're going to try to make that look simple. Now, what we want to write here is not this mess of code, is it? What we'd really like to write is to use the operators we have provided for our DSL, because that's obvious what we're saying here. it's anybody who reads that and has a little bit of background in computer science is going to understand, yeah, we're just splitting into a number, no problem. But that, of course, does not compile. The compiler is telling us, well, in order to do that, I need a rule sim, and I don't have one, so, not going to compile. That is interesting, though. What rule sim could we provide for that? Well, let's look at it. Num takes an f-type parameter, which is the type as which is going to be interpreted. And here we know we want to interpret it as a rule. So we're going to want to write a rule sim of rule. Because then it takes a value, which we know is an int, and a rule sim for that f here being rule. So we are going to need to write a rule sim of rule, which feels a little bit weird, right? Because, as I've said, a rule sim is an interpreter. So we're going to interpret a rule as a rule, which feels a little bit weird, but this is what the compiler is telling us to do, and the compiler often tends to be right. So let's follow through on that. How do you write a rule sim of rule? Well, let's take num, for example, and then generalize for the other ones. This is a boilerplate, lifted straight from the code we had before, where we have the f-type parameter as a corresponding rule sim and just the call to the corresponding num method. And that's all there is to it. We just do the same thing everywhere. We take the same boilerplate to begin with, and then call the same variable for variable, equal for equal, and end for end. And having done that, we can now simplify everything by replacing this mess of code with our operators. Quite a bit nicer, quite a bit more readable. And it works there, but it also works for that mess here. This immediately gets a lot more pleasant. Now, it's not perfect, I mean, it's still Scala, right? But you can read that quite a bit better than you could before. And I believe we're done here. What have we learned about deserialization? Well, compilation, serialization, and deserialization are essentially the same thing as with JDTs. Sure, we're manipulating functions, but we're basically doing the same thing. The syntax can be a little bit painful because there's, at least in the language I'm using, in the version of the language I'm using, there's still a little bit of boilerplate. But if you provide self-interpreters, so a rule sim of rule, for example, self-interpreter here is a word I came up with. It's not an official term. Don't quote me on that one, I just made it up for the talk. But if you provide one of these, then it takes a lot of the pain away because you can use your own syntax to help you. Do we have any questions at this point?
There was no questions. So somebody mentioned that this kind of feels like an identity sim, which I suppose is kind of what you're saying with the self-interpreter as well. Yeah,
yep, very much so.
I don't think there's any other questions. I'll give it 10 seconds, see if anyone else gets anyone in, and then we'll carry on.
All right. Now, you know what we're going to be doing, right? We are going to extend the language, because that's the entire point of using the tagless final encoding is to be able to do that. And why would we do that? Remember that we want to turn 1 equals 1 into true. But of course, we don't have the syntax yet. We don't know how to write bool of true. How would we do that? Well, and this is where the magic lays. How do we have var equals num and end? Well, we merely have them by virtue of having rules in here. So maybe we need to have something else that provides us with a bool. I'm not very creative with names, so I'm just going to call that bool sim, which represents the DSL for Booleans. And the DSL for Booleans is extremely simple. It just allows you to take a Boolean and lifts it, and just provides you support for Boolean literals. So given a Boolean value, it returns an f of Boolean. Of course, we need syntax for that. The bool operator that given a Boolean and a bool sim calls the bool method. And that's really all there is to it. We're done. We have added support for Booleans because here, well, we're going to need a bool sim because that's what we just wrote. And having done that, this compiles and will work exactly the way you want it to work. Why? By what magic does that work? Well, var equals num and end are just functions provided by rulesim. Bool is just a function provided by boolsim. So that's so far so good, but why does the end between the two compile? But there's no reason for it not to, because this here returns an f of Boolean. Category ID equals to 10 is it true or false. And bool returns an f of Boolean as well, and it's the same f. So of course n can compare an f of Boolean and an f of Boolean regardless of where that f came from. So this all compiles and run. This all compiles and run without having to modify any of the things we've defined before. We've just added one new layer of syntax on top of the existing one. We're going to give it a name. I'm calling it extended rule, which takes an f, so whatever we're going to evaluate the rule as. A rule sim and a bool sim, and that's what's extended about the rule. It's a regular rule that also has support for Booleans and returns an f of a. Done. Well, you recall that I said it was always worth providing self-interpreters to simplify the syntax, so we're going to do that here. There's something a little bit tricky here. I'm going to do my best to explain. I hope it works. How would you provide a rule sim of X rule, which, if I'm using simpler terms, means how would you provide an interpreter that, given a rule, interprets it as an extended rule? So how do you turn a rule that does not handle Booleans into a rule that does handle Booleans? Well, this is a rule. It takes an f, a rule sim, and yields an f of a. And that is how we define rules. But if we add a bool sim, then, and we still have this rule, because this is what we got from, right? We take a rule and we want to turn that into an extended rule. So we have that rule. We add a new bool sim parameter that turns it into an extended rule. But in order to evaluate the extended rule, all we have is our initial rule, which doesn't need Booleans. We know it doesn't need Booleans, because if it did, it would not be a rule, it would be an extended rule. It would be a rule that handles Booleans. It's not. So we can just completely ignore our Boolean parameter and just call our rule on the other parameters. And that gives us an extended rule. So in terms of code, we just go from a rule sim of rule, a rule that an interpreter that turns a rule into a rule. We rename that to a rule sim of extended rule, and we say, well, it's exactly the same thing as before, except everywhere where we used to expect a rule sim, we also take a bool sim. But we ignore it. We don't need it. We know we don't need it because we're going from a rule. By definition, a rule does not take Booleans. So people will provide us with ways of handling Booleans if we have them, but we don't, so we just ignore it. And that is our interpreter to turn a rule into an extended rule. Similarly, we need an interpreter to turn Booleans into extended rules, which works exactly the same way. We have the same boilerplate, and we ignore the rule sim because we do not need all the other interpreters. We only need the Boolean one. Right, and now we can try to pretty print things. We can try to take a rule and pretty print it, but that doesn't compile because, well, the compiler tells us exactly what's wrong, doesn't it? It tells us, well, I know how to do everything, but I do not know how to pretty print a Boolean because I do not have a bool sim of pretty. So let's write one. It's trivial. Given a Boolean, we just represent it as a string. Having done that, without recompiling anything from before, we get to pretty print our complex rule. Exactly the way we'd hope to. Compilation, same problem. We try to compile a complex rule into a function from doc to whatever, and that fails because we need a bool sim for that. And again, this is very easily done. We just define a bool sim that whatever the document we get, we ignore that and return the Boolean value, the Boolean constant that we were provided with. And that is enough. Now we can compile our complex rules, and if we evaluate it on our document, we get true, and again, if we modify 10 to 11, then we get false exactly like we'd want to. And finally, JSON encoding. This is where things are going to get a little bit weird. If you don't understand it, don't feel bad. That is kind of the point. You'll see why when we get to the end, but do need to give you this warning. This is going to get a little bit weird, a little bit hairy, but that is one of the problems with tagless final encoding. So there's no way of making this simple because it is not. JSON encoding. Well, we need an interpreter for, well, it's not going to compile because we need a bool sim of JSON rule. And this one is easily provided. Booleans are just encoded to JSON Boolean. So that's fine, isn't it? And when you evaluate our complex rule as a JSON rule, we get exactly the JSON that we wanted. So that's brilliant. And of course, we can define our encoder, which is the proxy, as before. That's basically boilerplate. And then if we evaluate a complex rule as a JSON object, we get the expected JSON object. Great. Now, decoder. If we want to decode some JSON to an extended rule event, well, we have only two scenarios for extended rule event, right? Variable and num. And both of these are already fully handled by our decoder of rule. So we can just rely on that. We can just say, whatever it is we get, just decode it as a, take the JSON, decode it as a rule event, and then evaluate that to an extended rule. Why does that work, that last line? Remember the self-interpreter that we wrote. So an interpreter that allows us to interpret a rule as an extended rule. This is exactly what's happening here. So that's going to compile, it does, and it's going to work exactly the way you want to, or at least it's going to look like that for a little while. Then the Booleans. Now the Booleans are a little bit tricky because we do have and equal, which are handled by the DSL, by our previous decoder for rule, but we also have Boolean. So we need to handle the Boolean case. The Boolean case is very easy, isn't it? We get a JSON Boolean, we turn that into a Boolean instruction in our language. Fine. And then anything else is already handled by our decoder for rule. So we'd write the same thing as before. Take the JSON, decode it as a rule, and turn that into an extended rule. And that looks like it all works. It looks just fine. And then you try to go for the round trip property, take your rule, serialize it to JSON, back to an extended rule, and you get an error. An especially annoying one at that, because it says invalid Boolean, true. Which is surprising, because true is clearly not an invalid Boolean, is it? So let's debug that. Let's see what happens here. When we try to decode that as an extended rule, so the way this works is when you try to decode something as something, we need an decoder for that output type. So we're going to look at the code of decoder extended rule of Boolean. So this knows how to decode Booleans or whatever else. We're trying to decode and, the root of our tree, so it's not a JSON Boolean, it's not a row Boolean, it's an other. So we're going to decode it as a rule of Boolean. We go to the rule of Boolean, decoder of rule of Boolean, which handles equals and other. Well, we are decoding and, aren't we? So this works, and eventually we're going to get to decoding the right-hand side, and we're going to decode that as a rule of Boolean, and this is important. It's a rule of Boolean. So when we get there, we're going to try to decode bool of true as a rule of Boolean. And, well, if we look at the decoder for that, it knows how to handle equals and another. And bool is not equals, it's not and, so it's got to be other, so it's got to be an error. This is a little bit mystifying. How did we get there? Well, look at it this way. When we have a decoder for extended rule of Boolean, it's got two scenarios. It can either decode straight to a bool, and it knows how to do that, or it's going to outsource its work to the decoder of rule of Boolean. Now that knows how to decode equals, which itself is going to decode the left-hand side, right-hand side as int, so it's going to outsource its work to the decoder of rule of int, or it's going to decode to an and. And that in turn relies on the decoder of rule of Boolean because the left-hand side and the right-hand side of an AND operations are Booleans. And therein lies the problem, because if you look at that here, once you're in rule of Boolean word, you can't get out anymore. You don't even know that extended rule exists anymore. So our problem is this arrow right here. We do not want to go back to rule of Boolean. Ideally, what we'd like to do is get rid of that arrow and replace it with that one. We'd like to go straight back to extended rule of Boolean. So our problem is here. Our problem with that is specifically in rule of Boolean, which kind of closes the word to any other implementation. How would you go about fixing that? Well, let's take Boolean decoder and see if we can rewrite it in a way that suits us better. First, to simplify things, and because it's more helpful, I'm going to replace that with its actual function type, which is JSON to error or rule. Right. Now, we know we specifically don't want to decode to a rule. We want to decode to a rule or an extended rule or whatever it is people need. So we need to abstract over the notion of what it decodes to. We need to decode to an F. So we get Fs everywhere now. What do we need to know about that F in order to do our work? Well, this is where, and then if you think about it, you're going to get it, but I don't like thinking too hard, and I just let the compiler do this for me. So the compiler is going to tell me, well, in order for you to be able to do that, to use that equals syntax, well, that requires a rule sim. So add a rule sim. Fair enough, done. If you want to decode stuff as an f of int, then you need a decoder of f of int. All right, there you go. I'm going to say that I need one of these. And similarly, in order to decode to an f of Boolean, you're going to need a decoder of f of Boolean. All right, let's have one of them as well. And that compiles. Which is pretty neat, because now our decoder of extended rule of Boolean, so the final thing we want, the thing that we want to decode both rules and extended rule, is entirely handled with this bit of code, where we say, I want to decode a Boolean to an extended rule. And the thing that's kind of nice here is that if you recall the parameters that decode bool take, the implicit parameters that it takes, well, it needs a rule sim, it needs a decoder of xrule event, but it also needs a decoder of xrule of Boolean. So this decoder is recursive, it's defined in terms of itself. And I find that this is kind of cool and kind of nice, because if you read the original paper in Tagless Final, the way they handled that recursion was by using the fixed point operator. And I've spent a certain amount of time trying to understand it and trying to understand what the code did. Never could. This I can get my head around. Right. And now that we have done that, it all works. We get exactly what we wanted. At what price? But we do get what we wanted. What have we learned? Well, we have learned that extending the language is done by adding layers of semantics. Sorry about that horrible word, not my fault, didn't come up with it. It does solve the expression problem, because we could do everything we had before without having to recompile anything. We could add new elements to our syntax without having to recompile any of the interpreters, and we could write new interpreters without having to change anything. So it does solve the expression problem. But deserialization in this encoding is its own special hell, and you don't want to do it unless you really have to. It's so hard to get right, so we got it wrong again. I'm not going to show you why, because I mean, we've done enough of that, but I'll leave that as an exercise to you. What did we get wrong? And the hint is, the way we've written it now, we have hard-coded it to extended rules. But maybe at some point we're going to write a third layer of semantic, I don't know, strings maybe, and then it's not extensible, is it? Because we have not made it extensible, we have not. Anyway, you work it out from these hints. I think I've talked enough about that specific problem. Right, and finally, the last bit, the pattern matching. How do you do pattern matching with functions? Well, that is a problem, isn't it? Remember what we want to do. We want to replace 1 equals 1 with Boolean. And with pattern matches, with JDTs, it was trivial. We looked for an EQ statement that contained 2 numbers. Very easy. Here, we're not working with data. We're working with functions. You can introspect on data. You cannot introspect on functions. You cannot look into a function and see what's inside of it. The only way you have of doing anything remotely like that is to evaluate the function on some value and see what comes out. Well, that is interesting though, because this is exactly what we're doing, right? Rule sim allows us to control what comes out of the rule. That is the purpose of the interpreter. So maybe we could evaluate a rule to give us information about what it contains. I'm going to call that context, for lack of a better word. And the context we need is, well, we need to know whether a rule is a number. Because when we're trying to simplify an equal statement, we need to look at its operands. Is that a number? Because if both are numbers, then I can simplify them. So we are going to need to know whether a rule is a number. There's this context for that. Context number, which also contains a value, because when we simplify, not only do we need to know that it's a number, we need to know what number it is to compare both of the operands. But for the rest, well, we don't care about the rest. We don't need to know whether it's an and, an equal, or a variable. We just need to know that it's not a number, because in that case, we can't really simplify our equal statement. So we can just say anything else. I don't need to know the details, it's just not a number. And we could easily write an interpreter for that. Would not be immediately useful, because it would give us the context of a rule rather than its simplified version. What we'll have is an interpreter that, given a rule, gives us its context. That's not what we want. What we really want, given a rule, we want an extended rule. So given a rule, something that doesn't actually handle Boolean, we want something that is a simplified, a canonical version of that rule, and that might contain Boolean, because 1 equals 1 turns to true. So what we really need then is something that returns both a context and an extended rule. A context to let us know whether we can simplify, an extended rule, which is a simplified version of whatever is going inside of there. And of course, functions can't return two values. But we have seen earlier in this talk, really quickly, but maybe you caught it, we have seen product types. Product types are an and between types. And this is what we want, isn't it? We want a context and an extended rule. So we're just going to return the product of context and extended rule, which in Scala we would write like this. The simplify is a product of a context and an extended rule of A. And this is really what we want to simplify to evaluate a rule to. Now, how would we write that? How would we write an interpreter that turns a rule into a simplifier? Well, in Tagless finals, this is done by providing a semantic. So here's a semantic. And how do we simplify a number? Well, we don't really simplify it. We can't make it simpler, but we need to give it context. The context is number. And the simplified expression, which is itself, is just a number. Similarly for variables, we can't really simplify it any further, but we do need to give it context, which here is other, and then the rest is follow the same logic as numbers. Now we have and, which is not much more interesting. Can't simplify it, we just need to say, well, it works exactly as a variable, it has no interesting context and it's just an and. And finally, the interesting parts, the equal statements. Now, we need to look at the context of the left-hand side and the right-hand side. Because if the left-hand side and the right-hand side are both numbers, then we can do our magic thing of replacing that with a Boolean. Here's how you implement it. If we have numbers both on the left and on the right, then we return something that is not a number, so the context is other, and whose value is the actual result of L equal to R. And then the last case, which is we have an equal statement, but at least one of the operands is not a constant. That is just left alone, so it follows the same logic as everything before that. And having done that, we can take our complex rule. Again, it's only complex in that it's 1 equals 1 at the end. And we can evaluate that in our simplify interpreter and pre-print that. And we get exactly what we wanted. The 1 equals 1 has been replaced with true. And well, this has shown us that Tagless final can do something like pattern matching, because this is what we've done. But it is achieved by manually tracking the context we're interested in. So whenever you want to do some pattern matching, you have to reinvent all the machinery that you need for that specific pattern match. So it is quite a bit less pleasant than pattern matching over JDTs. It is doable. You can definitely do it. We have done it. But that was a lot of work for something that was a one-liner before. Now, finally, what have we learned about Tagless final? Well, the first thing we learned is that it can do everything JDTs can. Well, we have done everything we did with JDTs with Tagless final, so it can. But it does make it a little bit harder. And it solves the expression problem. Now, that sounds like a lot of work for something that is essentially bragging rights, right? Now, I have written my DSL. It's a neat DSL, but what I have done is I've solved the expression problem with it. Now, it requires twice as much work, but I solved the expression problem. It doesn't sound very interesting, does it? But this is because we are taking I am purposefully taking a very narrow-minded view of what it is that we've done. We have solved the expression problem, but that's just in passing. What we have really done, and which is really interesting, is we have taken two distinct DSLs. The first one, rule, so variables, numbers, and equals, and an entirely different one, albeit a pretty simple one, the Boolean one, but still a completely different DSL, and we have composed them to build a completely new language, a more powerful language. So my example here of that is a little bit simple because it's a talk and it was quite long already. But if you're interested, there's a paper, I forgot the name, I think it's Quell, Queuel. I forget, I'll find the paper again and post it on Twitter. What it does, which I think is really brilliant, is it divides SQL into three distinct DSLs. I believe there's the aggregation DSL, the projection DSL, and the join DSL. And these are three different DSLs that they implement and work with, and then they compose them using Tagless final encoding and magic. We have these three brilliant DSLs, useful on their own, and then the magic happens and we get something even more powerful, which is the entire SQL language. So that is really powerful, because Tagless final allows you to compose DSLs, and that is the main selling point. Now, in closing, if you only remember one slide over all of these slides, admittedly, way too many slides, it's the one slide you should remember, because this is where I point out that I kept my promise to you in the first introduction, where I told you that by the end of the talk, you would know what a DSL is, and I hope, after all that you do. And I also told you would understand what a GADT encoding is, what a Tagless final encoding is, and how they differ and how they're similar. But you do. GADTs are data. They're easy to work with, but harder to extend. Tagless final, it's functions. It's harder to work with, but easier to extend. And I also told you, I promised you, that you'd encounter most of the main problems you're likely to encounter when you write a DSL, and solutions for them. And we have. We have seen how to evaluate, preprint, compile, rewrite, optimize, serialize, and deserialize expressions of a DSL. Which, when you have all of this down, you're pretty much sorted. You have done most of the thing you're ever likely to have to do with your DSL. Now, this was a lot of content, and unless you were already familiar with some or all of the material, you probably didn't get everything, and you probably won't remember everything. But that is fine. The point of this talk is not for you to become masters of this concept. The point of this talk is there are concepts that can be useful in a lot of different contexts. And there are ways of thinking about data and language that are not necessarily very intuitive. Thinking about a language as function application is a little bit weird. You have to be a little bit weird in the head to come up with it. But when you have, it opens up a whole world of possible applications. So now you know about these things, and my explanation should have at least given you an intuition of how and when to use them, so that next time you have a problem where this might actually be a valid solution, you remember that, not necessarily how to do it, but that it exists, and then look it up and see how to apply it to your problem. But if my explanations were not clear enough, or this talk was too long and I lost you by the end, you can always ask me some questions and I'll try to clarify. I think it's good that I'm done here because my voice is just about to give.
Absolutely. Yeah, there's only sort of two questions that are kind of general questions that I'm going to pull in. So, and then I think we're good. But thank you very much as well. That was really, really interesting. And I will admit I haven't got all of it, but definitely really enjoyed listening.
I think if I split it in more bite-sized chunks, it would be possible to get the entirety of it. But by the end of it, there's just a lot of content and concepts.
Absolutely. Cool. So yeah, I'll pull 2 questions, and then I think we're basically done. These kinds of DSLs are obviously incredible when dealing with user-written rules as an actual tiny programming language. However, do they have a place in other code bases? Yeah.
Well, oh, this camera is a little bit.
Yeah. Hold on. Let me. For now,
No,
while we're doing.
it's absolutely where, as and I'm familiar with my face. Right. Well, a lot of your code bases could probably do with some sort of very simple programming language that you could use to express things. Let's take an example. A very famous DSL. I don't know what software you use to edit and write code, but if you're a superior human being, you're using Emacs. And if you're using Emacs, then the entirety of the software has been written with a kind of DSL, Emacs Lisp, its own small programming language used to solve the problem. So that's an example. Of course, that's a little bit of a cheeky example because Lisp is a little bit more than a DSL, but even though. But, I mean, the example I gave, this is something that we have in production where we have experts of a given domain that must tell us how to exploit that domain, how to work with it. Giving them the tools to do so in a way that is non-ambiguous and as automated as possible is clearly beneficial. Now, you might work in a space where you are both the implementer and the expert. Then I'm not sure whether this would be useful, although giving yourself simplified tools so that you have a limited scope to reason with, but then you can reason about it better, might be interesting. But if you work in a space where you're not the expert of your domain, you're just a person who takes the expertise of somebody else and automates it, which I believe happens to be the case of a lot of people, then DSLs definitely have their place in your toolbox. Do they have their place in every single code base? Probably not. But my argument is, usually, if you try to think, would a DSL be useful here, then eventually you're going to find use cases and you'll be surprised at how useful they're going to prove to be and how much work they're going to automate away from you. When I say automate, I mean some other human is going to do it for you, which is, the next best thing.
Yeah, absolutely. And then I'll go for an easy one to finish up. Is the final source code available in Git anywhere?
Well, yeah, this one thing I might have wanted to say, if people were looking at these talks and trying to find errors in the code, this entire slide is the source code. It's actually interpreted and compiled when I generate the slide. So it all works, because otherwise you wouldn't have slides to see. I can absolutely provide you, it's not hard to guess. It's on my GitHub, and it's called DSL Tagless, something like that, but I can absolutely provide a link for that. Is there a way for me to put a comment here that people are going to see, or should I just tweet about it later? Or can I give it to you?
You can give it to me, and I can post it, and then Twitter as well if you want. That's totally fine.
There we go. Where do you want me? Should I just put it in the comments then?
Yes, that's fine.
Right. Yeah, not so fine. Apparently, I don't have the permissions to post comments.
God damn it! If you send it me.
Yeah, I'm doing that right now. Don't worry about it. Oh, there we go. You got it.
Excellent. There we go. I'll post that now as the Lambda Lounge account. There we are. That should appear on YouTube in just a moment. See if any more's come through. No. Okay. I think you've talked and talked and talked. I will not ask any more of you. No. Honestly, believe me,
I'm fine.
Wonderful.
Now, I do have a question for the attendants. Now, this talk is some tool I have been working on for a while, and one of the reasons I'm giving it here, other than showing it because it's cool, I'm actively looking for feedback on what works, what doesn't. So if you have any comments on things that were not clear, and even looking at the slide later, you have no idea what it is I'm doing, or if you think that the curves suck, or if you think that there are things that I should have talked about and I haven't, or vice versa, I'd be happy to hear any feedback that you have to help me make this better. The odds of it being picked by a conference are not very good because it's much too long, but I'd still quite like to see how I can improve it. So if you have any feedback, I would love to hear it.
Absolutely. Cool. So I will, hold on, I'll post the Discord link for anyone that wants to come and join on Discord after this chat. But yeah, thank you very much again. If we get any feedback as well, we'll pass it back to you.
I'd love to hear that.
Yeah.
I will not make it to Discord because it's quite late in France,
No
and
worries.
I haven't had dinner yet, so I'd really like to get some food inside of me now.
Absolutely. Well, yeah, thank you very much.
My pleasure. Thank you for having me.
Yeah. Final note for the Lambda Lounge people: we don't know what we're doing for next month yet, but we should be doing the what date will it be? The 21st of February will probably be the next talk. So yeah, we will be in touch about that. But thank you everybody, and thank you again for speaking.
My pleasure.
Cheers. Thanks.
Thank you.